Tonight, we begin with something you've seen countless times, but perhaps never truly understood. Step outside on any clear evening, look up at the stars scattered across the darkness, and you'll notice something remarkable. They dance, they shimmer, they seem to wink at you through the vast emptiness of space. This gentle flickering has captivated humans for thousands of years, inspiring poetry, navigation, and wonder. But what you're witnessing isn't the stars themselves changing. It's something far more fascinating, and tonight we'll explore the quiet science behind this celestial ballet. Before you settle in, take a moment to appreciate what we're about to discover together. The twinkling of stars isn't magic or mystery. It's a beautiful demonstration of physics in action, a gentle reminder that even the light from distant suns must travel through our world to reach your eyes. And in that journey, something extraordinary happens. Something that has taught us more about the universe than almost any other phenomenon we can observe from our small planet. So dim the lights, maybe open a window to let in the cool night air, and let's ease into this peaceful exploration of why stars flicker and what their gentle dance is trying to tell us about the cosmos. In a world where light travels at unimaginable speeds across incomprehensible distances, the simple act of a star's twinkle reveals secrets that took humanity centuries to understand. Every photon of starlight that reaches your eye has journeyed through space for years, decades, or even centuries, only to encounter one final obstacle just before reaching you. That obstacle is our atmosphere, the thin blanket of air that surrounds our planet and sustains all life as we know it. The story begins about 60 miles above your head, where Earth's atmosphere gradually thins into the vacuum of space. Here, in the thermosphere, temperatures can reach over 1,000 degrees, yet the air is so thin you wouldn't feel any heat at all. This is where starlight first encounters our planet's gaseous envelope, beginning a journey through layers of air that will transform that steady beam into the twinkling light we see below. As starlight descends through these atmospheric layers, it encounters something beautifully chaotic. Our atmosphere isn't uniform or still. It's a dynamic, ever-changing ocean of air masses with different temperatures, pressures, and densities. Warm air rises from sun-heated ground during the day, creating invisible columns that continue to churn even after sunset. Cold air descends from the upper atmosphere, creating downdrafts and mixing zones. Winds at different altitudes move air horizontally, creating shear layers where fast-moving air meets slower currents. Mountains interrupt airflow, creating turbulence that can extend for hundreds of miles downwind. All of this atmospheric activity creates what scientists call turbulent cells, pockets of air with slightly different properties than their neighbors. These cells are constantly forming, merging, breaking apart, and reforming in an endless dance of atmospheric dynamics. They're typically small, perhaps a few inches to a few feet across, and they last only seconds or minutes before dissipating. But during their brief existence, they act like tiny, ever-changing lenses floating in the sky above us. When a beam of starlight encounters one of these atmospheric lenses, something remarkable happens. The light bends. This bending, called refraction, occurs because light travels at different speeds through air of different densities. Just as a straw appears bent when placed in a glass of water, starlight appears to shift position as it passes through these atmospheric cells. But unlike the steady refraction of a straw in still water, these atmospheric lenses are constantly moving and changing shape. Imagine trying to read a book while looking through the gently rippling surface of a swimming pool. The words would appear to dance and shift, sometimes clear, sometimes distorted, as the water's surface creates an ever-changing pattern of lenses above the text. This is precisely what happens to starlight as it passes through our turbulent atmosphere. The star itself shines with perfect steadiness in space But by the time its light reaches your eyes, it has been gently tossed about by countless tiny atmospheric disturbances. The effect is most pronounced when you look at stars near the horizon. These stars must travel through much more atmosphere to reach you, passing through layers of air with greater temperature differences and more turbulence. A star directly overhead passes through perhaps 60 miles of atmosphere, while a star on the horizon must traverse hundreds of miles of air, encountering many more opportunities for its light to be bent and scattered. This is why stars twinkle more dramatically when they're low in the sky, especially during winter months when temperature differences between air masses are most extreme. The cold, dense air near the ground contrasts sharply with warmer air above, creating strong temperature gradients that bend starlight more dramatically. On particularly turbulent nights, stars near the horizon may appear to change colour rapidly, flashing red, white, and blue as different wavelengths of light are bent by different amounts. But here's something wonderful to consider. If you could somehow journey beyond Earth's atmosphere into the perfect vacuum of space, this twinkling would instantly cease. From the International Space Station, orbiting about 250 miles above Earth, stars appear as perfectly steady points of light. They don't twinkle at all. This tells us something profound about the nature of what we're observing. The flickering isn't coming from the stars themselves. It's entirely a product of our atmosphere's effect on their light. This realization fundamentally changed how we understand stellar observation. For centuries, astronomers struggled with the limitations imposed by atmospheric turbulence. Telescopes could be made larger and more precise, but the atmosphere imposed a fundamental limit on how clearly they could see. Stars that should appear as perfect points of light instead showed up as fuzzy, dancing blobs, making precise measurements nearly impossible. The breakthrough came with the development of adaptive optics, a technology that essentially removes the atmosphere's effects in real time. Using laser-guide stars and deformable mirrors, modern telescopes can now measure atmospheric distortions hundreds of times per second and correct for them instantly. The result is images from ground-based telescopes that rival those taken from space, revealing the universe with stunning clarity. But the story of stellar flickering goes far deeper than atmospheric effects. While our atmosphere creates the rapid twinkling we see with our eyes, many stars actually do change their brightness intrinsically. These changes happen on much longer timescales, from hours to years, and they reveal intimate details about stellar physics that atmospheric twinkling could never show us. Variable stars, as astronomers call them, are suns that physically change their brightness over time. Some expand and contract like cosmic hearts, pulsing with rhythms that can be measured and predicted. Others erupt in spectacular outbursts, briefly becoming thousands of times brighter before fading back to normal. Still others are locked in cosmic dances with companion stars, creating eclipses that dim their light at regular intervals. The discovery of variable stars revolutionized our understanding of the universe. In the early 20th century, astronomer Henrietta Swan-Leavitt was studying photographs of the Magellanic Clouds, two small galaxies visible from the southern hemisphere. She noticed that certain variable stars, called Cepheids, followed a remarkable pattern. The brighter the star's average luminosity, the longer its pulsation period. A Cepheid that took 30 days to complete one cycle of brightening and dimming was intrinsically more luminous than one with a 3-day period. This period luminosity relationship became one of astronomy's most powerful tools. By measuring how long a Cepheid takes to complete one pulsation cycle, astronomers can determine exactly how bright it actually is. By comparing this true brightness to how bright it appears from Earth, they can calculate its distance with remarkable precision. Cepheids became the cosmic lighthouses that allowed us to measure distances to nearby galaxies and eventually discover that the universe itself is expanding. The physical mechanism behind Cepheid pulsations is elegantly simple. These are massive stars nearing the end of their lives, with outer layers that have become unstable. As the star contracts under its own gravity, its interior heats up and produces more energy. This extra energy causes the outer layers to expand and cool, which reduces the energy production and allows gravity to pull the layers back inward. The cycle repeats endlessly, creating a stellar heartbeat that can be detected across millions of light years. Each type of variable star tells a different story about stellar evolution. RR Lyrae stars are older, less massive stars that have exhausted the hydrogen in their cores and are now burning helium. Their pulsations are faster than Cepheids, typically completing a cycle in less than a day. Long-period variables are aging red giants that pulse slowly over months or years as they shed their outer layers into space, eventually becoming white dwarf stars. Eclipsing binary stars represent another category entirely. These are pairs of stars orbiting so close together that, from our perspective, one star periodically passes in front of the other. The resulting eclipses create regular dips in brightness that reveal details about both stars' sizes, masses, and orbital characteristics. The famous star Algol, whose name means the demon star in Arabic, dims noticeably every 2 days and 20 hours as its fainter companion passes in front of the brighter primary star. Perhaps most dramatically, some stars undergo catastrophic changes that create novae and supernovae. A nova occurs when a white dwarf star in a binary system accumulates material from its companion until nuclear fusion ignites explosively on its surface. The star can briefly become 50,000 times brighter before fading back to its original state over weeks or months. Supernovae are even more spectacular, representing the complete destruction of a massive star in an explosion so bright it can outshine an entire galaxy. These stellar explosions have played a crucial role in creating the chemical elements necessary for life. The carbon in your body, the oxygen you breathe, the iron in your blood, all were forged in the nuclear furnaces of massive stars and scattered into space by supernova. In a very real sense, we are made of star stuff, connected to the cosmos through the ancient cycles of stellar birth, evolution, and death. Modern astronomy has revealed that virtually all stars vary in brightness to some degree. Our own sun fluctuates by about 0.1% over its 11-year magnetic cycle, a variation so small it requires sensitive instruments to detect. But even these tiny changes can affect Earth's climate and satellite communications, demonstrating how intimately connected we are to our nearest star's behavior. The study of stellar variability has also led to the discovery of exoplanets, worlds, orbiting other stars. When a planet passes in front of its host star as seen from Earth, it blocks a tiny fraction of the star's light, creating a minuscule but detectable dimming. By carefully monitoring thousands of stars for these transit signals, space missions like Kepler and TESS have discovered thousands of exoplanets, revealing that planetary systems are common throughout the galaxy. The precision required for these measurements is extraordinary. Detecting an Earth-sized planet orbiting a Sun-like star requires measuring brightness changes of just 0.008%, equivalent to detecting the dimming caused by a fruit fly crossing a car's headlight beam from several miles away. Yet modern instruments routinely achieve this level of precision, opening new windows into the diversity of planetary systems in our cosmic neighborhood. The delicate dance between starlight and our atmosphere has revealed another profound truth about the cosmos. Each wavelength of light carries its own unique signature, and as these different colors travel through our turbulent air, they bend by slightly different amounts. This phenomenon, called atmospheric dispersion, is why stars near the horizon sometimes appear to flash with rapid bursts of red, blue, and white light. Blue light, with its shorter wavelength, bends more readily than red light, as it passes through atmospheric pockets of varying density. When turbulence is particularly strong, you might notice a star seeming to separate into its component colors for brief moments, like a tiny prism flickering in the darkness. This color separation tells us something beautiful about the nature of starlight itself. Every star is not just a single point of white light, but rather a complex blend of many colors, each carrying information about the star's temperature, composition, and physical state. The spectrum of a star, spread out like a cosmic fingerprint, reveals secrets that would otherwise remain hidden across the vast distances of space. When astronomers capture starlight with their instruments and separate it into its component wavelengths, they discover dark lines scattered throughout the spectrum. These absorption lines occur when specific elements in the star's atmosphere absorb particular colors of light, creating a pattern as unique as a barcode. Hydrogen, the most abundant element in the universe, leaves its signature in the red part of the spectrum. Helium creates lines in the yellow and blue regions. Iron, calcium, sodium, and dozens of other elements each contribute their own distinctive marks. By studying these spectral fingerprints, astronomers can determine not just what a star is made of, but also how hot its surface is, how fast it's spinning, and whether it has a strong magnetic field. Temperature plays a particularly crucial role in determining a star's color and spectral characteristics. The hottest stars, with surface temperatures exceeding 30,000 degrees Fahrenheit, shine with an intense blue-white light. These stellar furnaces are so energetic that they ionize most elements in their atmospheres, creating relatively simple spectra dominated by hydrogen and helium lines. Cooler stars, like our Sun, with surface temperatures around 10,000 degrees, display yellow light and much more complex spectra filled with lines from dozens of different elements. The coolest stars, red giants and red dwarfs with surface temperatures below 6,000 degrees, glow with a ruddy light and show spectra so crowded with absorption lines, they resemble dense forests of dark marks. These cooler temperatures allow complex molecules to form in stellar atmospheres, adding even more spectral features that astronomers can decipher to understand stellar chemistry and physics. When atmospheric turbulence causes stars to twinkle, it affects each of these wavelengths slightly differently, creating the rapid color changes we sometimes observe. But this atmospheric interference, while beautiful to watch, has historically frustrated astronomers trying to make precise spectral measurements. The constant shifting and blurring of stellar images makes it difficult to capture the fine details needed for accurate analysis. This is why the development of space-based telescopes represented such a revolutionary advance in astronomy. Above Earth's atmosphere, instruments can capture stellar spectra with unprecedented clarity and precision. The Hubble Space Telescope, orbiting 340 miles above our planet, sees stars as perfectly steady points of light, their spectra unmarred by atmospheric distortion. This clarity has allowed astronomers to study stellar composition, temperature, and motion with accuracy that was impossible from the ground. The steadiness of starlight in space has also enabled the discovery of subtle variations that reveal the internal workings of stars themselves. While atmospheric twinkling happens on timescales of fractions of a second, real stellar variations occur much more slowly, over minutes, hours, days, or even years. These intrinsic changes in stellar brightness have opened entirely new windows into stellar physics. Some of the most fascinating stellar variations come from what astronomers call starquakes. Just as earthquakes result from the sudden release of built-up stress in our planet's crust, starquakes occur when the immense gravitational forces within a star suddenly overcome structural resistance. These stellar seismic events create pressure waves that travel through the star's interior, causing the entire surface to oscillate like a gently ringing bell. The Sun experiences millions of these tiny oscillations simultaneously, with different parts of its surface moving up and down by just a few miles every few minutes. By carefully measuring these solar oscillations, astronomers have been able to map the Sun's interior structure with remarkable precision, revealing details about temperature, density, and composition from the core to the surface. This field, called helioseismology, has transformed our understanding of how our nearest star works. Similar oscillations have been detected in thousands of other stars, each with its own unique seismic signature. Hot, massive stars ring with high-frequency oscillations that last only minutes. Cooler, less massive stars show longer period variations that can take hours to complete a cycle. By analysing these stellar heartbeats, astronomers can determine a star's mass, age, and internal structure without ever visiting these distant suns. The study of stellar oscillations has revealed that stars are far more dynamic than previously imagined. Rather than being static balls of gas shining steadily in space, they are complex, vibrating systems with intricate internal weather patterns. Convection currents carry energy from stellar cores to their surfaces, creating granulation patterns and magnetic field loops that constantly change the appearance of stellar surfaces. These internal processes affect not just how brightly a star shines, but also how its light varies over time. Young, rapidly rotating stars often show periodic brightness changes as dark spots and bright regions on their surfaces rotate in and out of view. Older stars may display more chaotic variations as their magnetic fields become more complex and their rotation slows down due to magnetic braking. The precise measurement of these subtle brightness variations has become one of modern astronomy's most powerful tools. Space missions like Kepler, TESS, and CoRoT monitor thousands of stars simultaneously, recording their brightness with extraordinary precision over months and years. The resulting light curves, graphs showing how stellar brightness changes over time, contain a wealth of information about stellar physics and evolution. A perfectly stable star would produce a flat light curve, showing no variations in brightness over time. But virtually no stars are perfectly stable. Even the most constant stars show tiny fluctuations caused by granulation, magnetic activity, and internal oscillations. More variable stars display dramatic changes that reveal ongoing processes of stellar evolution and interaction. The interpretation of stellar light curves requires sophisticated analysis and careful consideration of multiple physical processes. A gradual brightening over years might indicate that a star is evolving toward a later stage of its life cycle. Periodic variations could suggest the presence of star spots, internal pulsations, or an orbiting companion star. Sudden dramatic changes might herald explosive events like stellar flares or the beginning of a nova outburst. One of the most exciting applications of precise stellar photometry has been the detection and characterization of exoplanets. When a planet passes in front of its host star as seen from Earth, it blocks a tiny fraction of the stellar light, creating a barely detectable dimming. These transit events typically last only a few hours and reduce the star's apparent brightness by less than 1%. But modern instruments can reliably detect such minute changes. The shape and timing of transit light curves reveal detailed information about both the planet and its host star. The depth of the transit tells us the planet's size relative to the star. The duration of the transit indicates the planet's orbital speed and distance from the star. Multiple transits allow astronomers to determine the planet's orbital period and predict future transits with remarkable accuracy. Even more subtle effects can be detected with sufficiently precise measurements. If a planet has an atmosphere, starlight passing through it during transit will be filtered by atmospheric gases, creating tiny spectral signatures that reveal the atmosphere's composition. If multiple planets orbit the same star, their gravitational interactions create small timing variations in transit events that can reveal the masses and orbital characteristics of entire planetary systems. The success of transit photometry has fundamentally changed our perspective on planetary systems in the galaxy. Before the Kepler mission, we knew of only a few hundred exoplanets, most of them massive gas giants orbiting close to their stars. Kepler's exquisitely precise measurements revealed thousands of planets, including many Earth-sized worlds in potentially habitable orbits around their stars. This flood of exoplanet discoveries has shown that planetary systems are remarkably diverse and common throughout the galaxy. Some stars host multiple small planets packed into tight orbits. Others harbor giant planets with highly elliptical orbits that take them from scorching proximity to frozen distance from their stars. Still others show evidence of violent dynamical histories, with planets scattered into unusual orbits by gravitational encounters or stellar companion interactions. The statistical analysis of these exoplanet populations has provided crucial insights into how planetary systems form and evolve. The relative abundance of different planet types tells us about the efficiency of various formation mechanisms. The distribution of orbital periods reveals how planets migrate inward or outward after their initial formation. The correlation between planet properties and stellar characteristics helps us understand which types of stars are most likely to host Earth-like worlds. Perhaps most remarkably, the study of stellar flickering has revealed that our solar system may be somewhat unusual in its orderly arrangement of planets. Many exoplanetary systems show evidence of more chaotic histories, with hot Jupiters spiraling inward from distant orbits, super-Earths packed into configurations impossible in our system, and eccentric giant planets that would destabilize any Earth-like world's inhabitable zones. The gentle dance of starlight through our atmosphere, which began our exploration tonight, has thus led us to profound discoveries about the nature of stars, planets, and the cosmic environment in which we find ourselves. Each tiny fluctuation in stellar brightness carries information that spans the scale from atomic processes in stellar atmospheres to the grand architecture of planetary systems scattered throughout the galaxy. The precision required to extract this information from starlight is almost beyond comprehension. Detecting an Earth-sized planet requires measuring brightness, changes equivalent to a fruit fly passing in front of a car's headlight, as seen from dozens of miles away. Studying stellar oscillations means tracking brightness variations smaller than the flutter of a candle flame in a gentle breeze. Yet modern astronomical instruments routinely achieve these levels of precision, opening new windows into cosmic phenomena that were completely inaccessible just decades ago. As we continue to develop more sensitive detectors and more sophisticated analysis techniques, the information content of starlight continues to expand. Future space missions will be able to detect rocky planets in the habitable zones of nearby stars and analyze their atmospheres for signs of water vapor, oxygen, and other potential biosignatures. Ground-based telescopes equipped with advanced adaptive optics will directly image exoplanets and study their atmospheric composition and weather patterns. The story of stellar flickering thus represents one of astronomy's greatest success stories, transforming a simple observational curiosity into a comprehensive toolkit for understanding stars, planets, and the processes that govern cosmic evolution. From the ancient astronomers who first noticed that some stars change brightness over time, to the modern space missions that monitor hundreds of thousands of stars simultaneously, human ingenuity has converted the gentle dance of starlight into a vast library of cosmic knowledge. The next time you step outside on a clear evening and notice the stars twinkling overhead, remember that you are witnessing far more than a beautiful display. Each flicker carries information about the star itself, about our atmosphere, and about the fundamental physical processes that govern the universe. The starlight reaching your eyes has traveled across vast distances and countless years to deliver its cosmic message, filtered through the gentle lens of Earth's atmosphere in a process that connects us intimately to the broader cosmos of which we are all a part. This intimate relationship between starlight and atmosphere has guided human understanding for millennia, yet it wasn't until the late 19th century that astronomers began to truly comprehend what they were observing. The breakthrough came when scientists realized they could use the very distortions that frustrated their observations as tools for understanding both our atmosphere and the stars themselves. Consider the delicate precision required to measure stellar brightness variations. Early astronomers worked with photographic plates, exposing them for hours to collect enough starlight to study. These glass plates, coated with light-sensitive emulsions, captured not just the star's position, but also subtle variations in brightness that occurred over the exposure time. Patient observers would compare plates taken on different nights, looking for stars that appeared brighter or dimmer than before. The work was painstakingly slow and required extraordinary dedication. Astronomers would spend entire nights in cold observatories, guiding their telescopes by hand to track stars across the sky. They developed techniques for measuring stellar brightness with remarkable precision, using comparison stars of known brightness as references. This careful work laid the foundation for understanding that stars are not the unchanging beacons they appear to be, but dynamic systems undergoing constant evolution. The development of photoelectric photometry in the mid-20th century revolutionized this field. Instead of photographic plates, astronomers began using sensitive electronic detectors that could measure starlight intensity with unprecedented accuracy. These devices could detect brightness changes of less than 1%, revealing subtle variations that had been invisible to earlier observers. With these new tools, astronomers discovered that stellar variability is far more common and complex than anyone had imagined. Nearly every star shows some degree of brightness variation when observed with sufficient precision and over adequate time periods. These variations occur on timescales ranging from minutes to decades, each telling a different story about stellar physics and evolution. The shortest variations, lasting just minutes or hours, often result from stellar oscillations. These are pressure waves traveling through the star's interior, causing the entire surface to expand and contract slightly. The Sun experiences millions of these oscillations simultaneously, creating a complex pattern of surface motion that astronomers can measure by observing tiny Doppler shifts in the spectrum of sunlight. These solar oscillations have revealed the Sun's internal structure with extraordinary detail. Just as seismic waves from earthquakes allow geologists to map Earth's interior, stellar oscillations provide a window into regions of stars that could never be observed directly. The waves travel at different speeds through different materials, creating a complex interference pattern at the surface that encodes information about temperature, density, and composition throughout the star's interior. Longer period variations, occurring over days to months, often indicate more dramatic structural changes within stars. As stars age and exhaust the nuclear fuel in their cores, they undergo phases of instability that cause their outer layers to expand and contract rhythmically. These pulsations can be so regular that astronomers can predict when a star will reach maximum or minimum brightness years in advance. The red giant star Betelgeuse, visible in the constellation Orion, provides a spectacular example of this type of variation. This massive star, nearing the end of its life, pulsates with a period of about 6 years, changing its brightness by more than 50% during each cycle. The pulsations occur because the star's core has begun fusing heavier elements, creating an unstable balance between the inward pull of gravity and the outward pressure of nuclear fusion. When Betelgeuse contracts under its own gravity, the interior becomes denser and hotter, increasing the rate of nuclear reactions. This generates additional energy that causes the outer layers to expand and cool, reducing the energy production and allowing gravity to pull the star back together. The cycle repeats endlessly, creating the slow, majestic breathing of a dying giant star. These stellar pulsations are not merely academic curiosities. They represent one of the most important tools astronomers have for measuring cosmic distances. The relationship between a Cepheid variable's pulsation period and its intrinsic brightness is so precise that these stars serve as cosmic lighthouses, allowing us to map the three-dimensional structure of nearby galaxies. The discovery of this period luminosity relationship fundamentally changed our understanding of the universe's scale. In the 1920s, Edwin Hubble used Cepheid variables in the Andromeda Galaxy to prove that it lay far beyond the boundaries of our own Milky Way. This single observation doubled the known size of the universe and established that the fuzzy spiral nebulae visible through telescopes were actually distant galaxies containing billions of stars. But Hubble's work revealed something even more profound. By measuring the distances to many galaxies using Cepheid variables and comparing these distances to the galaxy's recession velocities, he discovered that the universe itself is expanding. Galaxies farther away are moving away from us faster than nearby ones, exactly as predicted by Einstein's theory of general relativity for an expanding universe. This discovery transformed cosmology from a philosophical discipline into an empirical science. The expansion of the universe implies that everything was once much closer together, leading naturally to the concept of the Big Bang. Measurements of the current expansion rate allow astronomers to calculate the age of the universe, estimate when the first stars formed, and predict the ultimate fate of cosmic evolution. All of this cosmic knowledge flows from the careful study of how starlight flickers and varies over time. The same atmospheric turbulence that creates the gentle twinkling we see with our eyes also provided the motivation for developing space-based astronomy, where stellar brightness can be measured with extraordinary precision. The Kepler Space Telescope, launched in 2009, monitored over 150,000 stars continuously for more than 4 years, measuring their brightness every 30 minutes with a precision of 20 parts per million. This level of accuracy is equivalent to detecting the dimming caused by a fruit fly crossing a car's headlight beam as seen from several miles away. Yet this precision was necessary to detect the tiny brightness dips caused by Earth-sized planets passing in front of their host stars. The data from Kepler and similar missions have revealed that planetary systems are astonishingly common throughout the galaxy. Nearly every star appears to host at least one planet, and many stars have multiple planets orbiting in complex dynamical configurations. The diversity of these systems has surprised astronomers, showing planetary architectures quite different from our own solar system. Some stars host super-Earths, rocky planets larger than our world but smaller than Neptune, orbiting so close to their stars that their surfaces would be molten rock. Others have hot Jupiters, massive gas giants that orbit their stars in just a few days, their atmospheres heated to thousands of degrees. Still others show evidence of planetary systems in the process of formation, with young stars surrounded by disks of gas and dust from which planets are condensing. The study of these exoplanetary systems has also revealed the subtle gravitational influences that planets have on their host stars. As a planet orbits its star, it causes the star to wobble slightly, moving toward and away from Earth by just a few meters per second. This tiny motion can be detected by measuring the Doppler shift in the star's spectrum, providing another method for discovering planets and measuring their masses. Even more remarkably, astronomers have learned to study the atmospheres of some exoplanets by analyzing how starlight passes through them during transit events. When a planet passes in front of its star, some of the star's light filters through the planet's atmosphere before reaching Earth. Different gases in the atmosphere absorb different wavelengths of light, creating a spectroscopic signature that reveals the atmospheric composition. Using this technique, astronomers have detected water vapor, methane, carbon dioxide, and other molecules in the atmospheres of dozens of exoplanets. They've also measured atmospheric temperatures, wind speeds, and cloud patterns on worlds hundreds of light years away. Some planets show evidence of extreme weather, with supersonic winds and rain made of molten glass or liquid iron. The precision required for these measurements pushes the boundaries of what's possible with current technology. Detecting atmospheric features in exoplanet spectra requires isolating signals that are millions of times fainter than the host star's light. Yet advances in detector technology and data analysis techniques continue to improve these capabilities, bringing us closer to the ultimate goal of detecting biosignatures in the atmospheres of potentially habitable worlds. The search for life beyond Earth represents perhaps the most profound application of stellar photometry and spectroscopy. Life, as we know it, requires liquid water, which can only exist within a narrow range of distances from a star where temperatures are neither too hot nor too cold. By studying the brightness variations of stars and the orbital characteristics of their planets, astronomers can identify worlds that might harbour conditions suitable for life. The detection of oxygen in an exoplanet's atmosphere would be particularly significant, as this reactive gas is continuously removed from atmospheres by chemical processes and can only persist if it's being replenished by biological activity. Similarly, the simultaneous detection of oxygen and methane would be even more compelling, as these gases react with each other and can only coexist if both are being produced continuously. Future space missions will extend these capabilities dramatically. The James Webb Space Telescope, with its large mirror and sensitive infrared detectors, can study the atmospheres of potentially habitable exoplanets in unprecedented detail. Planned missions like the Habitable Exoplanet Observatory will be designed specifically to detect and characterize Earth-like worlds around nearby stars, potentially providing the first definitive evidence of life beyond our solar system. The technology required for these future missions builds directly on the techniques developed for studying stellar variability. The same methods used to measure the tiny brightness changes caused by stellar pulsations are now being applied to detect the even smaller signals produced by Earth-sized planets. The same spectroscopic techniques used to determine stellar composition are now revealing the atmospheric chemistry of distant worlds. This progression from studying stellar flickering to searching for life represents one of the most remarkable developments in the history of science. In just a few decades, we've gone from barely being able to detect the largest exoplanets to characterizing the atmospheres of potentially habitable worlds. The precision of modern astronomical measurements would have seemed impossible to earlier generations of astronomers. Yet this technological revolution in astronomy is built on foundations that stretch back centuries. The patient work of early astronomers who catalogued variable stars by visual observation provided the framework for understanding stellar evolution. The development of photography and photoelectric photometry gave astronomers the tools to measure stellar brightness with increasing precision. The launch of space-based telescopes eliminated the atmospheric interference that had limited ground-based observations for centuries. Each generation of astronomers has built upon the work of their predecessors, gradually refining our understanding of how stars work and what their light can tell us. The flickering of stars that once seemed like simple atmospheric effects has revealed itself to be a complex phenomenon involving stellar physics, atmospheric science, and the fundamental processes that govern cosmic evolution. The story continues to unfold as new discoveries emerge from ongoing surveys and missions. The TESS mission, launched in 2018, is monitoring hundreds of thousands of stars across the entire sky, discovering new variable stars and exoplanets at an unprecedented rate. Ground-based surveys using automated telescopes scan millions of stars every night, looking for subtle changes that might indicate interesting astrophysical phenomena. Machine learning algorithms now analyze the vast data sets produced by these surveys, identifying patterns and anomalies that would take human astronomers decades to find manually. These artificial intelligence systems have discovered new types of variable stars, unusual planetary systems, and rare astronomical events that provide new insights into stellar and galactic evolution. The integration of data from multiple surveys and missions is creating an increasingly complete picture of how stars behave throughout their lives. Young stars show rapid variability as they settle onto the main sequence of hydrogen burning. Middle-aged stars like our Sun display relatively quiet behavior, punctuated by occasional flares and long-term magnetic cycles. Aging stars become increasingly unstable as they exhaust their nuclear fuel and begin the complex process of stellar death. This life cycle perspective has revealed that stellar variability is not just an interesting curiosity, but a fundamental aspect of how stars evolve and how they affect their surrounding environments. The energy output of variable stars influences the habitability of any planets that might orbit them. Stellar flares can strip away planetary atmospheres or deliver the energy needed to drive prebiotic chemistry. The heavy elements produced in stellar cores and dispersed by stellar winds and supernova explosions, provide the raw materials from which rocky planets and living organisms are constructed. Understanding stellar variability has thus become central to understanding the conditions that allow life to emerge and persist in the universe. The flickering of distant stars provides clues about whether those stars might host habitable worlds and what conditions any life forms might encounter on planets orbiting them. The philosophical implications of these discoveries are profound. The realization that we can study the internal structure of distant stars, characterize the atmospheres of exoplanets, and even search for signs of life beyond Earth, fundamentally changes our perspective on our place in the universe. We are no longer isolated observers of distant lights, but participants in a cosmic community connected by the universal physics that governs stellar evolution and planetary formation. The gentle twinkling of stars that has inspired poets and navigators throughout human history has revealed itself to be a vast library of information about the cosmos. Each flicker carries data about stellar composition, internal structure, evolutionary state, and the properties of any planets that might orbit nearby. The atmosphere that causes this twinkling, once seen as an obstacle to clear observation, has become a subject of study in its own right, revealing details about our planet's climate and weather patterns. As you drift towards sleep tonight, consider the remarkable journey that starlight takes to reach your eyes. Photons created in the nuclear furnace of a distant star travel across the vast emptiness of space for years or decades, carrying information about their stellar birthplace, encoded in their wavelength and intensity. They encounter Earth's atmosphere and are gently bent and scattered by turbulent air masses, creating the soft dancing light that has captivated human observers since the dawn of consciousness. In those final moments before the starlight reaches your retina, it passes through the same physical processes that allow astronomers to study stellar composition, discover exoplanets, and search for signs of life beyond Earth. The twinkling you see represents the intersection of cosmic physics and terrestrial meteorology, a gentle reminder of the interconnectedness of all natural phenomena. The next time you find yourself beneath a clear night sky, remember that the flickering stars above are not just beautiful decorations scattered across the darkness. They are distant suns, each with its own story of nuclear fusion, magnetic activity, and evolutionary change. Their light carries messages about the fundamental processes that govern the universe, written in a language that human ingenuity has learned to read with extraordinary precision and ever-increasing clarity. In the soft dance of starlight through our restless atmosphere, we find not just beauty, but understanding, not just mystery, but knowledge, not just distant lights, but cosmic neighbors whose stories are intimately connected to our own existence in this vast and wondrous universe. The technological revolution that allowed us to peer beyond atmospheric distortion has opened windows into stellar phenomena that our ancestors could never have imagined. When we remove the gentle interference of Earth's air, we discover that stars themselves are far from the steady beacons they appear to be from our planet's surface. They pulse, they oscillate, they breathe with rhythms that speak of the immense forces at work within their cores. In the perfect stillness of space, sensitive detectors can measure brightness changes so subtle they would be completely lost in atmospheric turbulence. These instruments reveal that our sun, seemingly so constant and reliable in its daily journey across our sky, actually varies in brightness by tiny amounts that follow complex patterns tied to magnetic activity deep within its interior. Solar flares erupt from its surface with energies that dwarf all human technology combined. Yet these dramatic events cause brightness changes of less than 0.1%. The precision required to study these phenomena pushes the boundaries of measurement itself. Modern space telescopes can detect brightness variations equivalent to a single candle being extinguished in a football stadium filled with blazing lights, observed from hundreds of miles away. This extraordinary sensitivity has revealed that the cosmos is far more dynamic and interconnected than anyone suspected just decades ago. Consider the delicate process by which we've learned to read the stories written in stellar light. Each photon carries information about its birthplace encoded in its wavelength and energy. When these photons reach our detectors, sophisticated instruments spread the light into its component colors, revealing absorption lines that mark the presence of specific elements in the star's atmosphere. Hydrogen leaves its signature in deep red wavelengths. Helium creates lines in yellow and blue regions. Iron, calcium, magnesium, and dozens of other elements each contribute their own unique patterns. The strength and width of these spectral lines tell us about conditions within the stellar atmosphere. Strong lines indicate abundant elements, while weak lines suggest scarcity. Broad lines reveal rapid rotation that Doppler shifts the light, while narrow lines indicate slowly spinning stars. The overall color distribution tells us about surface temperature, with blue stars burning at over 50,000 degrees, and red stars glowing at temperatures cooler than a candle flame. When we combine this spectroscopic information with precise brightness measurements over time, a complete picture of stellar physics begins to emerge. Stars are not simple balls of gas shining steadily in space, but complex systems with intricate internal weather patterns, magnetic field structures, and evolutionary changes that play out over millions of years. The internal structure of a typical star resembles a series of nested spheres, each with its own temperature, density, and physical processes. At the center lies the nuclear furnace where hydrogen fuses into helium, releasing the energy that powers the star's light. This core region operates under conditions so extreme that matter exists in states impossible to reproduce on Earth. Temperatures reach tens of millions of degrees, and pressures exceed billions of times our atmospheric pressure. Surrounding the core is the radiative zone, where energy slowly diffuses outward through countless interactions with matter. A single photon created in the core may take hundreds of thousands of years to work its way to the surface, scattered and reabsorbed countless times along the way. This region acts like a vast insulating blanket, moderating the flow of energy from the nuclear furnace to the outer layers. Near the surface lies the convection zone, where hot material rises and cool material sinks in vast circulation patterns. These convective currents create the granulation patterns visible on the sun's surface, where cells of rising hot gas appear bright against the darker lanes of descending cooler material. The constant churning of this convective layer drives magnetic field generation and creates the complex activity cycles that cause long-term brightness variations. The visible surface, or photosphere, is where the star's light finally escapes into space. Despite being called a surface, this region is actually a thin layer of gas so tenuous that it would be considered a perfect vacuum by terrestrial standards. Yet this delicate boundary between star and space is where all the information we receive about distant suns originates. Above the photosphere lies the stellar atmosphere, including the chromosphere and corona, regions of increasingly hot and tenuous gas that extend far into space. These outer layers are heated by magnetic fields and shock waves from below, creating conditions that can be hotter than the visible surface itself. The interaction between magnetic fields and atmospheric gases creates the spectacular solar flares and coronal mass ejections that occasionally disrupt communications and navigation systems on Earth. Each layer of stellar structure contributes to the star's overall brightness and how that brightness changes over time. Variations in nuclear burning rates affect energy production in the core. Changes in opacity influence how efficiently energy flows through the radiative zone. Convective patterns alter the transport of energy to the surface. Magnetic activity modulates the appearance of the photosphere and atmosphere. When we observe brightness variations from space-based telescopes, we're seeing the combined effects of all these internal processes. The challenge for astronomers lies in separating these different contributions to understand what's happening inside stars we can never visit. This is where the study of stellar oscillations becomes crucial to our understanding. Just as seismic waves from earthquakes reveal Earth's internal structure, pressure waves traveling through stellar interiors create oscillations that we can observe as tiny brightness and velocity variations at the surface. These stellar seismic waves are generated by turbulent convection in the outer layers of stars, creating a constant background of acoustic noise that propagates throughout the stellar interior. Different oscillation modes travel through different parts of the star, sampling conditions at various depths and latitudes. Some waves penetrate all the way to the core, while others are reflected back from intermediate layers. By analyzing the frequencies and amplitudes of thousands of simultaneous oscillations, astronomers can reconstruct the internal structure of distant stars with remarkable precision. The Sun serves as our laboratory for understanding these processes. Solar oscillations were first detected in the 1960s, when astronomers noticed that the Sun's surface moves up and down with periods of about 5 minutes. Subsequent observations revealed millions of oscillation modes operating simultaneously, creating a complex symphony of stellar vibrations that encode information about conditions throughout the solar interior. These solar oscillations have revealed that the Sun's core rotates faster than its surface, that the convection zone extends about 1/3 of the way to the center, and that the nuclear burning rate varies slightly over the 11-year solar cycle. They've also provided precise measurements of the Sun's internal temperature, density, and composition that have tested and confirmed our theoretical models of stellar structure. Similar techniques are now being applied to thousands of other stars. The Kepler Space Telescope, originally designed to search for exoplanets, proved equally valuable for studying stellar oscillations. By monitoring stars continuously for months or years with unprecedented precision, Kepler revealed that asteroseismology could be applied to main sequence stars, red giants, and even some white dwarf stars. Each type of star displays its own characteristic oscillation patterns. Hot, massive stars show high-frequency oscillations driven by radiation pressure in their outer layers. Cool, low-mass stars exhibit slower oscillations powered by convective turbulence. Red giant stars, with their extended atmospheres and dense cores, display mixed modes that sample both the stellar interior and the tenuous outer layers. The study of red giant oscillations has been particularly revealing. These aging stars have exhausted the hydrogen in their cores and are now burning helium in a shell surrounding an inert carbon-oxygen core. The oscillations can distinguish between stars burning helium in their cores and those burning it in shells, providing crucial information about stellar evolution that was previously impossible to obtain. White dwarf stars, the dense remnants left behind when Sun-like stars exhaust their nuclear fuel, also show oscillations that reveal their internal structure. These stellar corpses are slowly cooling and crystallizing, and their oscillations provide insights into the physics of matter under extreme conditions. Some white dwarf oscillations are so regular they rival atomic clocks in their precision, making them valuable for testing theories of gravity and stellar evolution. The application of asteroseismology has revolutionized our understanding of stellar ages. Traditional methods for estimating stellar ages relied on comparing observed properties with theoretical evolutionary tracks, but these techniques were often uncertain by factors of 2 or more. Asteroseismic measurements can determine stellar ages with uncertainties of just 10 or 20%, transforming our ability to study galactic evolution and exoplanet formation timescales. The precision of these age determinations has profound implications for understanding planetary systems. Knowing the precise age of a star tells us how long any planets orbiting it have been exposed to stellar radiation, how the star's brightness and magnetic activity have evolved over time, and how much longer the star will remain stable enough to support life on nearby worlds. This connection between stellar physics and planetary habitability represents one of the most exciting frontiers in modern astronomy. The same space missions that study stellar oscillations are simultaneously discovering thousands of exoplanets, creating unprecedented opportunities to understand the relationship between stellar properties and planetary system architecture. The brightness variations caused by planets passing in front of their stars provide complementary information to astroseismic studies. While oscillations tell us about the star's internal structure and evolution, planetary transits reveal the orbital dynamics and atmospheric properties of the worlds orbiting nearby. Together, these techniques are painting a comprehensive picture of how stellar systems form and evolve over cosmic time. The detection of planetary atmospheres through transit spectroscopy represents perhaps the most remarkable application of precision stellar photometry. When a planet passes between its star and Earth, some of the star's light filters through the planet's atmosphere before reaching our telescopes. Different gases in the atmosphere absorb specific wavelengths of light, creating a transmission spectrum that reveals the atmospheric composition. Using this technique, astronomers have detected water vapor, carbon dioxide, methane, and other molecules in the atmospheres of dozens of exoplanets. They've measured atmospheric temperatures ranging from hundreds to thousands of degrees, discovered high-altitude clouds and hazes, and even detected weather patterns on worlds hundreds of light-years away. The most exciting prospects lie in applying these techniques to potentially habitable worlds, orbiting nearby stars. Future space telescopes will have the sensitivity to detect biosignature gases like oxygen and ozone in the atmospheres of Earth-sized planets, in the habitable zones of their stars. The simultaneous detection of oxygen and water vapor would provide compelling evidence for biological processes on distant worlds. These observations will require extraordinary precision and stability. Detecting biosignatures in exoplanet atmospheres means measuring spectral features that are millions of times fainter than the host star's light. The techniques being developed for these future missions build directly on the methods refined for studying stellar oscillations and variability. The technological challenges are immense, but the scientific payoff could be transformational. Within the next 2 decades, we may have definitive evidence for life beyond our solar system, discovered through careful analysis of how starlight filters through distant atmospheres. This would represent the culmination of centuries of progress in understanding stellar physics and the information encoded in starlight. The philosophical implications of such a discovery would be profound, but they would build naturally on the scientific foundation laid by generations of astronomers who patiently studied the flickering of stars. From the earliest observers who noticed that some stars change brightness over time, to modern space missions that monitor hundreds of thousands of stars simultaneously, each generation has contributed to our growing understanding of cosmic processes. The story of stellar variability illustrates how scientific knowledge builds cumulatively over time. Early visual observations established the basic phenomena. Photographic techniques allowed systematic surveys and precise measurements. Electronic detectors provided the sensitivity needed to study subtle variations. Space-based observations eliminated atmospheric interference and revealed phenomena invisible from the ground. Each technological advance opened new windows into stellar physics and revealed previously unknown aspects of how stars work. The same pattern continues today as new missions and instruments push the boundaries of precision and sensitivity ever further. Machine learning algorithms now analyze vast data sets automatically, identifying patterns and anomalies that would take human astronomers decades to find. The integration of data from multiple surveys and missions is creating an increasingly complete picture of stellar behavior throughout the galaxy. Young star-forming regions reveal how stellar variability evolves as stars settle onto the main sequence. Surveys of old stellar populations show how variability changes as stars age and exhaust their nuclear fuel. Studies of different stellar masses and compositions reveal how these properties influence variability patterns. This comprehensive view of stellar behavior is transforming our understanding of galactic evolution. Stars are not passive objects that simply shine steadily for billions of years. They are dynamic systems that inject energy and heavy elements into their surroundings through stellar winds, flares, and eventual death. The cumulative effects of stellar feedback shape the structure of galaxies and influence the formation of subsequent generations of stars and planets. The study of stellar variability has also revealed unexpected connections between different astronomical phenomena. The same magnetic processes that create solar flares also drive stellar winds that can strip away planetary atmospheres. The heavy element enrichment from stellar nucleosynthesis influences both stellar evolution and planet formation. The gravitational waves produced by merging stellar remnants carry information about the most extreme physics in the universe. These connections illustrate the interconnected nature of cosmic processes. Understanding any one phenomenon requires knowledge of many others, creating a web of relationships that spans from quantum physics to cosmology. The flickering of stars, which might seem like a simple observational curiosity, touches on fundamental questions about the nature of matter, energy, space, and time. And, as our techniques for studying stellar variability continue to improve, we're beginning to probe phenomena that operate on the very edge of detectability. Gravitational waves from merging black holes and neutron stars create tiny distortions in space-time that can be measured by laser interferometers. These cosmic collisions, predicted by Einstein's theory of general relativity, represent the ultimate stellar endpoints and provide unique insights into the physics of extreme gravitational fields. The detection of gravitational waves has opened an entirely new window into the universe, complementing the electromagnetic observations that have been astronomy's primary tool for centuries. Future space-based gravitational wave detectors will be sensitive to lower frequency waves produced by merging white dwarf stars and intermediate mass black holes, phenomena directly connected to stellar evolution and death. The combination of gravitational wave astronomy with traditional electromagnetic observations creates opportunities for multi-messenger science, where the same cosmic events are studied using different types of signals. The merger of two neutron stars can be detected as gravitational waves, gamma-ray bursts, optical transients, and radio afterglows, each providing different information about the physics of these extreme events. These multi-messenger observations are revealing that the universe is far more dynamic and violent than previously imagined. Stellar explosions, black hole mergers, and neutron-star collisions occur regularly throughout cosmic history, each event briefly outshining entire galaxies and enriching the universe with heavy elements necessary for planet formation and life. The study of these extreme events builds directly on the foundation of stellar variability research. The same techniques used to study Cepheid pulsations are now applied to detect the optical signatures of neutron star mergers. The precision photometry developed for exoplanet detection is used to study the light curves of supernovae and gamma-ray burst afterglows. This continuity between different areas of astronomical research illustrates the cumulative nature of scientific progress. Each new discovery builds on previous knowledge, often in unexpected ways. The patient work of cataloguing variable stars in the early 20th century laid the groundwork for measuring cosmic distances and discovering the expansion of the universe. Modern surveys searching for exoplanets are simultaneously discovering new types of variable stars and providing insights into stellar physics. The vast databases created by these surveys contain information that will be analyzed for decades to come. Machine learning algorithms are just beginning to reveal patterns in stellar behavior that were invisible to traditional analysis methods. As these techniques become more sophisticated, they will undoubtedly uncover new phenomena and connections that will shape future research directions. The democratization of astronomical data through online archives and citizen science projects is also transforming how research is conducted. Amateur astronomers now have access to professional quality datasets and can contribute to scientific discoveries from their homes. Citizen science projects have discovered hundreds of new variable stars, identified unusual transient events, and helped classify millions of galaxies. This collaborative approach to astronomy reflects the universal human fascination with the cosmos and our place within it. The same curiosity that drove ancient astronomers to map the positions and brightness of stars continues to motivate people around the world to contribute to our understanding of the universe. The technology has changed dramatically, but the fundamental questions remain the same. As we look toward the future, the study of stellar variability will continue to evolve and expand. Next-generation space telescopes will monitor millions of stars with unprecedented precision, revealing subtle phenomena that are currently beyond our reach. Advances in detector technology will push the limits of sensitivity and enable new types of measurements that we can barely imagine today. The integration of artificial intelligence into astronomical research will accelerate the pace of discovery and reveal patterns in complex data sets that would be impossible to find manually. These AI systems will not replace human astronomers, but will serve as powerful tools for exploring the vast parameter space of cosmic phenomena. Perhaps most importantly, the search for biosignatures in exoplanet atmospheres will represent the ultimate application of precision stellar photometry and spectroscopy. The techniques developed for studying stellar oscillations and variability will be applied to the most profound question in science. Are we alone in the universe? The answer, when it comes, will likely be written in the subtle variations of starlight filtered through distant atmospheres. The gentle flickering of stars that has guided this exploration tonight represents far more than a beautiful atmospheric phenomenon. It connects us to the fundamental processes that govern cosmic evolution, from the nuclear fusion in stellar cores to the formation of planetary systems capable of supporting life. Each tiny variation in stellar brightness carries information about temperatures, pressures, magnetic fields, and chemical compositions that span the entire range of cosmic environments. The precision with which we can now measure and interpret these variations would seem miraculous to earlier generations of astronomers. Yet this technological achievement rests on centuries of patient observation, theoretical development, and instrumental innovation. The same scientific method that allowed ancient astronomers to predict eclipses and navigate by the stars has evolved into a sophisticated toolkit for understanding the universe on scales from individual atoms to cosmic structures spanning billions of light years. As you rest beneath the gentle glow of distant suns tonight, remember that their light carries stories of cosmic evolution, written in a language that human ingenuity has learned to read with extraordinary fluency. The twinkling that once seemed like simple atmospheric interference has revealed itself to be a window into the deepest secrets of stellar physics, planetary formation, and perhaps even the existence of life beyond our small world. In the soft dance of starlight through our restless atmosphere, we find not just beauty, but profound connection to the cosmic processes that created the elements in our bodies, shaped the evolution of our galaxy, and continue to govern the formation of new stars and planets throughout the universe. The next time you notice the gentle flickering of stars overhead, you're witnessing the intersection of earthly and cosmic phenomena, a reminder that we are not separate from the universe we observe, but intimately connected participants in the ongoing story of cosmic evolution. The flickering stars above carry messages from distant worlds and distant times, their light encoded with information about the fundamental forces that shape reality itself. In learning to read these cosmic signals, we have not only expanded our knowledge of the universe, but also discovered our own place within the vast web of relationships that connect every atom, every planet, every star, in an elegant tapestry of physical law and cosmic evolution. Tonight, as stellar photons complete their long journeys from distant nuclear furnaces to reach your eyes, They bring with them the accumulated wisdom of generations of human observers who looked up at the same flickering lights and wondered what stories they might tell. Through patience, ingenuity, and the gradual refinement of our tools and techniques, we have learned to listen to these whispered secrets from the cosmos, discovering in the process that the universe is far stranger, more beautiful, and more interconnected than our ancestors ever dared to imagine. The gentle twinkling that has closed our exploration tonight serves as a peaceful reminder that science and wonder are not opposing forces, but complementary ways of appreciating the remarkable universe in which we find ourselves. In the careful measurement of stellar brightness variations, we find both precise knowledge and profound mystery. In the study of atmospheric turbulence, we discover both practical understanding and poetic beauty. In the search for distant worlds, we pursue both scientific discovery and the age-old human dream of finding our place among the stars. As sleep approaches and consciousness fades into the realm of dreams, let the steady rhythm of stellar oscillations and the gentle flutter of atmospheric turbulence carry you into peaceful rest, knowing that the cosmic dance above continues through the night, writing new chapters in the eternal story of stars and planets, light and shadow, knowledge and wonder that connects all of us to the vast, mysterious, and utterly magnificent universe we call home. Home. The subtle dance of electromagnetic radiation continues around us, even as we drift towards sleep, carrying with it the accumulated knowledge of countless stellar generations. In the profound stillness that follows understanding, we find ourselves connected to processes that span the breadth of cosmic time, from the first moments when hydrogen began its slow transformation into the heavier elements that would eventually form planets, atmospheres, and the very neurons that now contemplate these distant lights. Consider the extraordinary journey that has brought us to this moment of comprehension. The carbon atoms in your body were forged in the nuclear furnaces of massive stars that lived and died billions of years ago. The oxygen you breathe was created in the final moments of stellar collapse, scattered into space by supernova explosions that briefly outshone entire galaxies. The iron in your blood was synthesized in the cores of dying giants and dispersed through stellar winds that enriched the interstellar medium with the raw materials for new worlds. This cosmic recycling continues today in star-forming regions scattered throughout our galaxy, where gravity slowly gathers the debris of ancient stellar explosions into new concentrations of matter. In these stellar nurseries, temperature and pressure gradually increase until nuclear fusion ignites, creating fresh suns that will shine for millions or billions of years. Each new star begins its own unique story of evolution, destined to contribute its own chapter to the ongoing narrative of cosmic chemical enrichment. The light from these distant stellar furnaces carries forward through space at the ultimate speed limit of the universe, unchanged and unchanging until it encounters the gentle turbulence of our atmosphere. In those final moments before reaching our eyes, this ancient starlight becomes a messenger, telling us stories of stellar birth, evolution, and death, written in the universal language of physics. The precision with which modern astronomers can read these stellar messages would seem impossible to earlier generations of skywatchers. Where ancient observers saw only points of light that wandered across the celestial sphere, we now detect the subtle signatures of stellar rotation, magnetic activity, internal oscillations, and evolutionary changes. Where medieval astronomers noted only that some stars appeared brighter or dimmer on different nights, we now measure brightness variations of parts per million and use them to map the internal structure of distant suns. This transformation in our understanding reflects not just advances in technology, but fundamental changes in how we approach the study of nature. The same careful observation and mathematical analysis that revealed the laws governing planetary motion have been applied to understanding stellar structure, galactic dynamics, and the expansion of the universe itself. Each generation of astronomers has built upon the work of their predecessors, gradually assembling a comprehensive picture of cosmic evolution. The statistical analysis of large stellar populations has revealed patterns and relationships that were invisible when studying individual stars in isolation. Surveys monitoring millions of stars simultaneously have shown that stellar variability follows predictable patterns related to mass, age, and evolutionary state. Young stars show rapid chaotic variability as they settle into stable nuclear burning. Middle-aged stars like our Sun display relatively quiet behavior punctuated by magnetic cycles and occasional flares. Aging stars become increasingly unstable as they exhaust their nuclear fuel and begin the complex transition to stellar death. These population studies have also revealed the subtle environmental effects that influence stellar evolution. Stars in dense galactic clusters evolve differently than isolated field stars, affected by gravitational interactions and close encounters with neighboring systems. Stars in the metal-rich regions near galactic centers follow different evolutionary paths than those in the metal-poor galactic halo, where the lack of heavy elements affects opacity and energy transport. The cumulative picture emerging from these studies shows that stellar evolution is not a simple, predictable process, but a complex interplay of internal physics and external environmental factors. Each star's evolutionary path is influenced by its initial mass, composition, rotation rate, and magnetic field strength, as well as interactions with companions, interstellar material, and the galactic gravitational field. Understanding these complexities has profound implications for our models of galactic evolution and planet formation. The timing and location of stellar death events determine when and where heavy elements are injected into the interstellar medium. The frequency and intensity of stellar flares affect the habitability of nearby planets. The gravitational influence of stellar remnants shapes the dynamics of planetary systems over cosmic time. The search for potentially habitable exoplanets must therefore consider not just the current properties of host stars, but their entire evolutionary history and future prospects. A planet orbiting a star that will become unstable and variable within a few 100 million years faces very different long-term prospects than one orbiting a star that will remain stable for billions of years. The techniques developed for studying stellar variability have also found unexpected applications in other areas of astrophysics. The same methods used to detect exoplanet transits are now being applied to study asteroid occultations, providing precise measurements of asteroid sizes and shapes. The algorithms developed for analyzing stellar light curves are being used to identify variable quasars and track the growth of supermassive black holes in distant galaxies. These cross-disciplinary applications illustrate the interconnected nature of astronomical research. Advances in one area often lead to breakthroughs in seemingly unrelated fields, as new techniques and technologies find applications beyond their original purpose. The precision photometry developed for exoplanet detection has revolutionized the study of stellar oscillations, stellar rotation, and magnetic activity cycles. The integration of multi-wavelength observations has added additional layers of complexity and richness to our understanding of stellar variability. Stars that appear constant in visible light may show dramatic variations in ultraviolet or X-ray wavelengths, revealing high-energy processes in stellar corona and chromospheres. Infrared observations can detect variations caused by dust formation and destruction in stellar atmospheres, while radio observations reveal the effects of stellar magnetic fields on surrounding plasma. Future space missions will extend these multi-wavelength capabilities to unprecedented levels of sensitivity and precision. The James Webb Space Telescope, with its large mirror and sensitive infrared detectors, will be able to study stellar variability in the infrared with precision comparable to what Kepler achieved in visible light. This will open new windows into stellar physics and allow detailed studies of cool stars, brown dwarfs, and stellar formation processes. The technological challenges faced by these future missions continue to push the boundaries of what's possible in space-based astronomy. Achieving the stability needed for precise photometry requires extraordinary engineering, with spacecraft components maintained at constant temperatures and isolated from vibrations and thermal fluctuations. The detectors must be calibrated to parts per million accuracy and corrected for systematic effects that could mimic astronomical signals. Yet these technical challenges pale beside the scientific opportunities they create. Future surveys will monitor hundreds of millions of stars simultaneously, creating databases of unprecedented size and scope. Machine learning algorithms will sift through this vast amount of data, identifying patterns and relationships that would take human astronomers centuries to discover manually. The democratization of astronomical data through online archives and citizen science projects continues to expand the community of people contributing to stellar variability research. Amateur astronomers equipped with modest telescopes and modern cameras can now make measurements that rival professional observations from just decades ago. Online collaboration tools allow distributed teams of observers to coordinate long-term monitoring campaigns and share data in real time. This collaborative approach reflects the global nature of modern astronomy and the universal human fascination with understanding our cosmic environment. The same curiosity that motivated ancient astronomers to track the motions of planets continues to drive thousands of amateur and professional observers to monitor the brightness changes of distant stars. The philosophical implications of this work extend far beyond the technical details of stellar physics. The realization that we can study the internal structure of stars, characterize the atmospheres of distant planets, and search for signs of life throughout the galaxy fundamentally changes our perspective on humanity's place in the universe. We are no longer isolated observers of distant lights, but participants in a cosmic community connected by universal physical laws. The precision with which we can now measure stellar properties also provides increasingly stringent tests of our theoretical models of stellar structure and evolution. When observations disagree with predictions, they point toward new physics or previously unknown processes that must be incorporated into our understanding. The history of astronomy is filled with such discoveries, where careful observations revealed phenomena that required fundamental revisions to existing theories. The study of stellar variability continues to surprise us with unexpected discoveries and connections. Recent observations have revealed that some stars undergo sudden changes in their rotation rates, possibly due to internal magnetic field reorganization. Others show evidence of star-spot cycles that operate on much longer timescales than the 11-year solar cycle, suggesting that stellar magnetic dynamos can operate in ways we don't yet fully understand. The detection of stellar flares on nearby red dwarf stars has important implications for the habitability of planets orbiting these long-lived, low-mass stars. While red dwarfs remain stable for hundreds of billions of years, making them attractive targets for searches for long-term habitability, their tendency to produce powerful flares could strip away planetary atmospheres or sterilize planetary surfaces. Understanding these stellar hazards requires long-term monitoring campaigns that track flare frequency and intensity over years or decades. The statistical analysis of large samples of red dwarf stars is beginning to reveal patterns in flare activity related to stellar age, rotation rate, and magnetic field strength. This information is crucial for assessing which types of stars are most likely to host habitable planets. The study of white dwarf stars has also revealed unexpected complexity in these supposed stellar remnants. While white dwarfs were once thought to be simple cooling objects with no internal energy sources, precision photometry has revealed that many show regular brightness variations caused by non-radial oscillations. These pulsations probe the internal structure of white dwarf stars and provide insights into the physics of matter under extreme density. Some white dwarf stars also show evidence of ongoing accretion from surrounding debris disks, possibly the remnants of destroyed planetary systems. The brightness variations caused by this accretion provide information about the composition and structure of these debris disks, offering glimpses into the final fate of planetary systems around dying stars. The connection between stellar evolution and planetary system architecture continues to reveal new complexities as observational capabilities improve. The discovery that some hot Jupiter exoplanets have highly misaligned orbits suggests that planetary systems can undergo dramatic reorganization throughout their histories. Gravitational interactions with binary star companions, close encounters with passing stars, and the evolving gravitational field of the host star as it loses mass can all affect planetary orbits over cosmic time. Understanding these dynamical processes requires combining observations of exoplanet properties with detailed knowledge of stellar evolution and galactic dynamics. The same precision astrometry used to detect stellar oscillations can measure tiny orbital motion of nearby stars, revealing the gravitational influence of massive planets or stellar companions. The integration of these different observational techniques is creating an increasingly complete picture of how stellar and planetary systems evolve together over cosmic time. Young systems show evidence of ongoing planet formation and orbital migration. Middle-aged systems, like our own solar system, appear relatively stable, with planetary orbits that have remained largely unchanged for billions of years. Old systems around evolved stars show evidence of dramatic changes as stellar mass loss and stellar evolution alter the gravitational environment. These studies have profound implications for understanding the long-term prospects for life in the universe. If planetary systems are subject to ongoing dynamical instability, then the conditions necessary for complex life may be much rarer and more fragile than previously thought. Conversely, if most planetary systems achieve long-term stability, then the prospects for sustained biological evolution may be much more favorable. The search for biosignatures in exoplanet atmospheres represents the ultimate application of precision stellar photometry and spectroscopy. The techniques that began with simple observations of stellar brightness variations have evolved into sophisticated tools capable of detecting the chemical fingerprints of life in the atmospheres of distant worlds. Future space missions designed specifically for this purpose will require extraordinary stability and precision. The detection of oxygen and water vapor in Earth-sized exoplanet atmospheres means measuring spectral features that are millions of times fainter than the host star's light. Achieving this sensitivity requires careful control of systematic errors and sophisticated techniques for separating planetary signals from stellar variability. The development of these capabilities represents one of the greatest technical challenges in modern astronomy. Success will require advances in detector technology, spacecraft stability, data analysis techniques, and theoretical understanding of both stellar and planetary atmospheres. Yet the potential scientific payoff makes these challenges worthwhile, as the discovery of biosignatures would fundamentally change our understanding of life's prevalence in the universe. The philosophical implications of such a discovery would extend far beyond astronomy and astrobiology. Confirming that life exists elsewhere in the universe would affect fields ranging from theology to psychology, challenging our understanding of humanity's uniqueness and our relationship to the cosmos. The knowledge that we are not alone would likely inspire new questions about the nature of consciousness, intelligence, and our responsibilities as cosmic citizens. Yet even if biosignatures remain elusive, the search itself continues to advance our understanding of stellar and planetary physics. Each new exoplanet discovery adds to our knowledge of planetary formation and evolution. Each new measurement of stellar properties refines our models of stellar structure and evolution. Each advance in observational techniques opens new possibilities for future discoveries. The cumulative impact of these investigations extends far beyond the immediate scientific results. The technologies developed for space-based astronomy find applications in fields ranging from medical imaging to communications. The data analysis techniques pioneered for astronomical surveys are now used in genomics, climate science, and artificial intelligence research. The international collaboration required for major astronomical projects serves as a model for addressing global challenges that transcend national boundaries. The same cooperative spirit that enables astronomers from dozens of countries to work together on understanding stellar evolution could be applied to addressing climate change, developing sustainable energy sources, and exploring our own solar system. The educational impact of astronomical discoveries continues to inspire new generations of scientists and engineers. The wonder and excitement generated by exoplanet discoveries and stellar studies motivates students to pursue careers in science, technology, engineering, and mathematics. The same curiosity that drives astronomical research also motivates innovation in fields ranging from medicine to environmental science. As observational capabilities continue to improve and data analysis techniques become more sophisticated, the pace of discovery in stellar astronomy shows no signs of slowing. Future surveys will monitor billions of stars simultaneously, creating datasets of unprecedented size and complexity. New analysis techniques will reveal patterns and relationships that are currently invisible to our best methods. The integration of artificial intelligence into astronomical research will accelerate this process, enabling the automated discovery of new types of variable stars, unusual planetary systems, and rare astronomical phenomena. These AI systems will not replace human astronomers, but will serve as powerful tools for exploring the vast parameter space of cosmic phenomena. Perhaps most importantly, the techniques developed for studying stellar variability will continue to find new applications in unexpected areas of astrophysics. The same methods used to detect exoplanet transits are now being applied to study gravitational microlensing, stellar occultations, and even the shadows of black holes. The precision photometry developed for asteroseismology is being used to study the rotation of asteroids, the structure of binary star systems, and the variability of active galactic nuclei. This cross-pollination of techniques and ideas illustrates the interconnected nature of modern astronomy and the cumulative way that scientific knowledge develops. Each advance builds on previous discoveries, often in ways that were impossible to anticipate when the original work was done. The patient observations of variable stars by early 20th century astronomers laid the groundwork for measuring cosmic distances and discovering the expansion of the universe, applications that were unimaginable when the work began. The story of stellar variability research thus serves as a powerful example of how basic scientific research can lead to profound discoveries that transform our understanding of the universe. The flickering of stars that once seemed like a simple observational curiosity has revealed the internal structure of stellar cores, the existence of thousands of exoplanets, and the fundamental processes that govern cosmic evolution. As we rest beneath the gentle light of these distant suns, we can appreciate both the beauty of their flickering and the extraordinary scientific story that this simple phenomenon has revealed. The same atmospheric turbulence that creates the twinkling we see with our eyes also motivated the development of space-based astronomy, leading to discoveries that have revolutionized our understanding of stars, planets, and our place in the cosmic community. The precision with which we can now measure and interpret stellar brightness variations represents one of humanity's greatest intellectual achievements. From visual estimates of stellar brightness made by ancient astronomers to space-based measurements precise to parts per million, we have developed tools that can probe the deepest secrets of stellar physics and reveal the presence of Earth-like worlds around distant stars. This remarkable journey from simple observation to profound understanding illustrates the power of the scientific method and the cumulative nature of human knowledge. Each generation of astronomers has contributed to our growing comprehension of cosmic processes, building on the work of their predecessors while developing new tools and techniques that enable ever more precise and revealing observations. The gentle flickering of stars that has guided our exploration tonight serves as a peaceful reminder that the universe is both more complex and more beautiful than our ancestors ever imagined. In the careful study of these subtle brightness variations, we have discovered not just new astronomical phenomena, but new ways of thinking about our relationship to the cosmos and our responsibility as conscious observers of the universe. The soft dance of starlight through our atmosphere connects us to processes that span the entire range of cosmic scales and time periods. The nuclear fusion in stellar cores, the turbulent motion of atmospheric gases, the gravitational interactions of planetary systems, and the evolution of galaxies all contribute to the flickering patterns we observe in the night sky. Understanding these connections has revealed that we are not separate from the universe we study, but intimately connected participants in the ongoing story of cosmic evolution. The elements in our bodies were forged in stellar cores and dispersed by stellar death. The energy that powers our civilization comes ultimately from nuclear fusion in our sun. The stable planetary environment that enables complex life exists because of delicate balances in stellar and planetary physics. This perspective encourages both humility and wonder as we contemplate our place in the cosmic order. We are simultaneously insignificant specks in a vast universe and remarkable products of cosmic evolution, capable of understanding the very processes that created us. The flickering stars above remind us that we are temporary arrangements of stellar debris that have somehow achieved consciousness and curiosity about the universe from which we emerged. As consciousness fades and the gentle rhythm of stellar oscillations carries you toward peaceful sleep, let the quiet knowledge of these cosmic connections provide comfort and perspective. The same physical laws that govern the nuclear fusion in distant stellar cores also govern the chemical processes in your brain that create thoughts and dreams. The same gravitational forces that hold planetary systems together also guide the circulation of blood through your body. In the soft glow of starlight filtering through our restless atmosphere, we find not just beauty and wonder, but profound evidence of our connection to the cosmos and our place in the grand story of stellar birth, evolution, and death that continues to unfold across the galaxy. The flickering stars carry messages of cosmic history and cosmic future, written in the universal language of physics and decoded by generations of patient observers who looked up at the same lights and gradually learned to read the stories written in their gentle dance. Tonight, as stellar photons complete their ancient journeys to reach your eyes, they bring with them the accumulated wisdom of cosmic evolution and human discovery, reminding us that in understanding the flickering of distant stars, we have also discovered something profound about ourselves and our remarkable ability to comprehend the universe of which we are all part. In this quiet moment between wakefulness and sleep, surrounded by the gentle light of distant suns, we rest in the peaceful knowledge that we belong to something far greater and more beautiful than we could ever fully understand, yet wonderfully accessible to our curiosity, our instruments, and our patient desire to know. The gravitational dance between binary stars creates some of the most predictable and precisely measurable variations in stellar brightness we can observe from Earth. When two stars orbit each other in a plane that aligns with our view, we witness a celestial clockwork of remarkable precision. As the dimmer companion passes in front of the brighter primary star, the combined light reaching our telescopes decreases in a pattern as regular as a cosmic metronome. These eclipsing binary systems have taught us extraordinary details about stellar properties that would otherwise remain hidden. By carefully timing the eclipses and measuring how the brightness changes during each event, astronomers can determine the sizes, masses, and surface temperatures of both stars with remarkable accuracy. The duration of the eclipse reveals the orbital speed and separation of the stellar pair. The depth of the brightness drop tells us the relative sizes of the two stars. Some of the most famous variable stars in our sky are actually eclipsing binaries masquerading as single stars. Algol, known to ancient astronomers as the demon star, because of its regular dimming every 2 days and 20 hours, puzzled observers for centuries before its true nature was understood. The star seemed to wink at Earth with disturbing regularity, dimming to 1/3 its normal brightness before returning to full luminosity exactly 69 hours later. The mystery was solved when astronomers realized they were observing two stars locked in gravitational embrace, with the fainter star periodically blocking the light from its brighter companion. This discovery opened an entirely new window into stellar physics, allowing precise measurements of stellar properties that had previously been impossible to determine. The study of eclipsing binaries has revealed that stars often form in pairs or groups, rather than in isolation. More than half of all stars in our galaxy are members of multiple star systems, bound together by gravity in complex orbital dances that can last for billions of years. These gravitational relationships profoundly influence stellar evolution, as stars in close binary systems can exchange material, alter each other's rotation rates, and even trigger explosive events when one star transfers matter onto its companion. The precision with which we can measure eclipsing binary properties has made them invaluable tools for testing our theoretical models of stellar structure and evolution. When observations disagree with predictions, they point toward new physics or previously unknown processes that must be incorporated into our understanding. The masses and radii determined from eclipse measurements provide fundamental benchmarks against which all theories of stellar evolution must be tested. Modern surveys monitoring millions of stars simultaneously have discovered thousands of new eclipsing binary systems, revealing an extraordinary diversity in stellar partnerships. Some systems contain stars so close together they complete an orbit in less than an hour, their surfaces nearly touching as they whirl around their common center of mass. Others consist of stars separated by distances comparable to the orbit of Pluto, taking decades or centuries to complete a single orbit. The most exotic systems contain compact objects like white dwarf stars, neutron stars, or even black holes orbiting normal stars. When material from the normal star falls onto the compact companion, it can create spectacular outbursts of X-rays and gamma rays that briefly make the system millions of times brighter than our Sun. These cataclysmic variable stars show us stellar evolution in its most extreme and violent forms. The study of these systems requires international coordination and long-term monitoring campaigns that span decades. Amateur astronomers around the world contribute crucial observations, timing eclipses with precision that rivals professional observatories. This collaborative effort has created databases containing millions of eclipse measurements that continue to refine our understanding of stellar physics. The technological demands of this work have driven innovations in detector design and data analysis that find applications far beyond astronomy. The same techniques used to measure stellar brightness variations are now employed in medical imaging, environmental monitoring, and communications technology. The precision timing required for eclipse studies has contributed to advances in atomic clocks and satellite navigation systems. As we transition from the realm of stellar pairs to the broader cosmic environment, we encounter phenomena that operate on much larger scales of space and time. The interstellar medium, the thin gas and dust that fills the space between stars, also affects the light we receive from distant stellar sources. This tenuous material can absorb, scatter, and polarize starlight in ways that reveal the composition and structure of our galactic neighborhood. Dust grains floating in interstellar space preferentially absorb blue light, while allowing red wavelengths to pass through relatively unimpeded. This selective absorption causes distant stars to appear redder than they actually are, an effect called interstellar reddening. By carefully analyzing the colors of stars at different distances, astronomers can map the three-dimensional distribution of dust clouds throughout our galaxy. The same dust that reddens starlight also scatters it, causing some stars to appear to twinkle more than others, depending on the amount of intervening material. Stars seen through dense dust clouds show more erratic brightness variations as swirling currents in the interstellar medium create changing patterns of absorption and scattering. These variations occur on much longer timescales than atmospheric scintillation, typically over months or years rather than seconds. Interstellar gas clouds can also affect stellar spectra in subtle but measurable ways. Cold hydrogen and other elements in space absorb specific wavelengths of starlight, creating additional absorption lines that appear superimposed on the stellar spectrum. By studying these interstellar absorption features, astronomers can determine the chemical composition, temperature, and motion of gas clouds lying between us and distant stars. The discovery that our galaxy contains vast quantities of invisible dark matter has added another layer of complexity to our understanding of stellar environments. While dark matter doesn't interact directly with light, its gravitational influence affects the motion of stars and gas throughout the galaxy. Precision measurements of stellar positions and velocities have revealed the presence of this mysterious material and provided clues about its distribution and properties. The gravitational influence of dark matter creates subtle effects that can be detected in the motion of stars over long periods of time. Stars in the outer regions of our galaxy orbit faster than would be possible if only the visible matter we can see were providing the gravitational force. This observation, repeated in galaxy after galaxy, provides compelling evidence for the existence of dark matter and reveals its crucial role in shaping the structure of the universe. These large-scale gravitational effects also influence stellar evolution in ways that are only beginning to be understood. The tidal forces exerted by the galaxy's gravitational field can trigger star formation in gas clouds, affect the stability of planetary orbits, and even influence the internal structure of stars themselves. The cosmic environment in which a star forms and evolves plays a subtle but important role in determining its properties and evolutionary path. The study of stellar populations in different galactic environments has revealed systematic differences in stellar properties related to local conditions. Stars in the dense central regions of galaxies show different age distributions and chemical compositions than those in the sparse outer regions. These variations provide insights into how galaxies form and evolve over cosmic time. The precision required to detect these subtle environmental effects pushes observational capabilities to their limits. Space-based astrometry missions can measure stellar positions with accuracies of a few millionths of an arc-second, equivalent to detecting the width of a human hair as seen from a distance of 1,000 miles. These extraordinary measurements reveal the tiny motions caused by gravitational interactions with unseen companions, dark matter concentrations, and the overall galactic gravitational field. Future space missions will extend these capabilities even further, monitoring the positions and brightnesses of billions of stars with unprecedented precision. The resulting data sets will contain information about stellar physics, galactic dynamics, and dark matter distribution that will take decades to fully analyze and understand. Machine learning algorithms are already being developed to identify patterns in these vast databases that would be impossible for human astronomers to find manually. The integration of position measurements with brightness variations and spectroscopic data is creating three-dimensional maps of stellar properties throughout our local galactic neighborhood. These maps reveal how stellar formation rates, chemical composition, and evolutionary states vary with location in the galaxy. They also provide crucial constraints on models of galactic evolution and the distribution of dark matter. As observational capabilities continue to improve, the boundary between stellar astronomy and galactic astronomy becomes increasingly blurred. Understanding individual stars requires knowledge of their galactic environment, while understanding galactic evolution requires detailed knowledge of stellar physics. This interconnected approach reflects the growing recognition that astronomical phenomena operate on multiple scales simultaneously. The same gravitational forces that govern the internal structure of stars also determine the large-scale structure of galaxies and galaxy clusters. The nuclear fusion processes that power stellar luminosity also enrich the interstellar medium with heavy elements necessary for planet formation. The magnetic fields that create stellar activity cycles also influence the propagation of cosmic rays throughout the galaxy. These connections illustrate the fundamental unity of physical processes operating throughout the universe. The laws of physics that govern the behavior of matter and energy in stellar cores also apply to the largest structures in the cosmos. Understanding any one astronomical phenomenon requires appreciation of its connections to processes operating on both smaller and larger scales. The philosophical implications of these discoveries continue to evolve as our observational capabilities expand. The realization that we can study the internal structure of distant stars, map the distribution of invisible dark matter, and trace the chemical evolution of entire galaxies fundamentally changes our perspective on humanity's place in the cosmic order. The precision with which we can now measure astronomical phenomena also provides increasingly stringent tests of our most fundamental theories about the nature of space, time, matter, and energy. Einstein's theory of general relativity, formulated over a century ago, continues to be tested and confirmed by observations of stellar motion, gravitational lensing, and the propagation of gravitational waves from merging stellar remnants. These tests of fundamental physics, using astronomical observations, represent one of the most remarkable achievements of human intellectual development. The ability to use observations of flickering starlight to probe the deepest questions about the nature of reality demonstrates the power of the scientific method and the extraordinary reach of human reasoning. The study of stellar variability has thus evolved from simple brightness measurements to a comprehensive toolkit for understanding the universe on scales ranging from stellar interiors to cosmic structure. Each tiny fluctuation in starlight carries information that connects us to processes operating throughout the cosmos, from the quantum mechanics governing nuclear fusion to the general relativistic effects of massive black holes. Modern astronomical surveys continue to discover new types of variable stars and unexpected connections between different astrophysical phenomena. Machine learning algorithms sift through vast databases of stellar observations, identifying patterns and anomalies that reveal new insights into stellar physics and galactic evolution. The pace of discovery shows no signs of slowing as detector technology continues to improve and analysis techniques become more sophisticated. The democratization of astronomical data through online archives and citizen science projects has created opportunities for people around the world to contribute to these discoveries. Amateur astronomers equipped with modern digital cameras can now make observations that rival professional measurements from just a few decades ago. Students and hobbyists analyze real astronomical data and occasionally make discoveries that advance our understanding of stellar behavior. This collaborative approach reflects the universal human fascination with understanding our cosmic environment and our place within it. The same curiosity that motivated ancient astronomers to track the changing brightness of stars continues to drive thousands of observers to monitor the subtle variations in stellar light that reveal the hidden workings of the universe. The technological innovations developed for astronomical research continue to find applications in fields ranging from medicine to communications. The sensitive detectors used to measure stellar brightness variations have been adapted for medical imaging systems. The data analysis techniques developed for identifying variable stars are now used in genomics, climate research, and artificial intelligence applications. The international cooperation required for major astronomical projects serves as a model for addressing global challenges that transcend national boundaries. The same collaborative spirit that enables astronomers from dozens of countries to work together on understanding stellar evolution could be applied to addressing climate change, developing sustainable technologies, and exploring our own solar system. The educational impact of astronomical discoveries continues to inspire new generations of scientists, engineers, and curious individuals. The wonder generated by learning that we can study the internal structure of distant stars and detect planets orbiting other suns motivates students to pursue careers in science and technology. This intellectual excitement represents one of the most valuable products of astronomical research. As we look toward the future, The study of stellar variability will continue to evolve in directions that are difficult to predict, but certain to be surprising. New detector technologies will enable observations that are currently impossible. New theoretical insights will reveal connections between phenomena that now seem unrelated. New analysis techniques will extract information from existing data that we cannot currently access. The search for biosignatures in the atmospheres of potentially habitable exoplanets represents one of the most exciting frontiers in this ongoing exploration. The same precision photometry techniques that revealed the internal structure of pulsating stars are now being used to detect the tiny atmospheric signals that might indicate biological activity on distant worlds. Future space missions designed specifically for this purpose will require technological capabilities that push the boundaries of what is currently possible. The stability and precision needed to detect biosignatures in exoplanet atmospheres exceed the requirements of any previous astronomical mission. Success will require advances in detector design, spacecraft engineering, and data analysis that will likely find applications throughout science and technology. The potential discovery of life beyond Earth would represent the culmination of centuries of progress in understanding stellar physics and the information encoded in starlight. Such a discovery would fundamentally change our understanding of life's prevalence in the universe and our place within the cosmic community. Yet even if biosignatures remain elusive, the search itself continues to advance our understanding of stellar and planetary physics. Each new measurement adds to our knowledge of how stars and planets form and evolve. Each technological advance opens new possibilities for future discoveries. Each theoretical insight reveals new connections between different aspects of cosmic evolution. The cumulative impact of this research extends far beyond the immediate scientific results. The perspective gained from studying our cosmic environment affects how we think about our own planet, our species, and our responsibilities as conscious observers of the universe. The realization that Earth is one small world, orbiting an ordinary star in a typical galaxy, encourages both humility and wonder. The precision with which we can now measure and interpret stellar properties would seem miraculous to earlier generations of astronomers. Yet this extraordinary capability rests on centuries of patient observation, theoretical development, and technological innovation. The same scientific method that allowed ancient observers to predict eclipses has evolved into a sophisticated framework for understanding the universe on scales from subatomic particles to cosmic structures spanning billions of light years. The gentle flickering of stars that began our exploration continues to serve as a peaceful reminder of the deep connections between earthly and cosmic phenomena. The atmospheric turbulence that creates the twinkling we observe with our eyes operates according to the same physical principles that govern stellar interiors, galactic dynamics, and the expansion of the universe itself. In the quiet moments before sleep, when consciousness begins to fade and the busy thoughts of the day gradually subside, the knowledge that we are connected to these vast cosmic processes can provide a sense of perspective and tranquility. The carbon atoms in our bodies were forged in the cores of ancient stars. The oxygen we breathe was created in stellar explosions that enrich the galaxy with heavy elements. The energy that powers our thoughts ultimately derives from nuclear fusion in our sun. These connections remind us that we are not separate from the universe we study, but integral parts of the ongoing story of cosmic evolution. The same physical laws that govern the flickering of distant stars also govern the biochemical processes that sustain life on Earth. The same gravitational forces that hold stellar systems together also guide the circulation of blood through our bodies and the electrical impulses that create consciousness. The study of stellar variability has revealed that change and stability exist in delicate balance throughout the cosmos. Stars maintain their basic properties for billions of years while undergoing subtle internal changes that eventually lead to dramatic evolutionary transformations. Planetary systems persist for cosmic ages, while being slowly reshaped by gravitational interactions and stellar evolution. This cosmic perspective on change and permanence offers insights that extend beyond astronomy into philosophy, psychology, and the human experience. The realization that we exist during a brief moment in cosmic history, on a small planet orbiting an ordinary star, while being composed of materials created in stellar cores billions of years ago, provides a framework for understanding our place in the larger scheme of existence. The precision required to study stellar variability has taught us that even the smallest measurements can reveal profound truths about the nature of reality. The detection of brightness changes smaller than 1 part in a million has led to discoveries about stellar structure, exoplanets, and the fundamental constants that govern physical processes throughout the universe. This lesson about the importance of precision and careful measurement applies equally well to other areas of human endeavor. The same attention to detail that enables astronomers to detect the subtle signatures of planets around distant stars can guide us in understanding complex systems, ranging from climate patterns to biological processes to social dynamics. The collaborative nature of modern astronomical research also provides a model for addressing challenges that require cooperation across traditional boundaries. The same international partnerships that enable space missions and ground-based surveys could be applied to developing sustainable technologies, understanding Earth's climate system, and exploring our own solar system. The technological innovations driven by astronomical research continue to find unexpected applications in medicine, communications, environmental monitoring, and many other fields. The detectors developed for measuring stellar brightness variations are now used in medical imaging systems. The algorithms created for analyzing astronomical data are applied in genomics and artificial intelligence research. These connections between basic research and practical applications illustrate the unpredictable nature of scientific discovery. Investigations undertaken purely to satisfy human curiosity about the universe often lead to technological advances that benefit society in ways that could not have been anticipated when the original work began. The educational value of astronomical research extends beyond the training of professional scientists to include the broader impact on scientific literacy and public understanding of the natural world. The excitement generated by discoveries about exoplanets, stellar evolution, and cosmic structure helps maintain public support for science and encourages young people to pursue careers in science and technology. The aesthetic dimension of astronomical discovery also enriches human culture in ways that are difficult to quantify, but deeply meaningful. The beautiful images captured by space telescopes, the elegant mathematical relationships that describe stellar behavior, and the profound insights into our cosmic origins all contribute to the human experience in ways that transcend purely practical considerations. As we drift towards the peaceful state that precedes sleep, the gentle rhythm of stellar oscillations and the soft flutter of atmospheric turbulence can serve as reminders of the vast, beautiful, and comprehensible universe in which we find ourselves. The same physical processes that create the twinkling we observe continue operating throughout the night, across the galaxy, and throughout the cosmos. The stars above us pulse with internal oscillations that reveal their deepest secrets to patient observers. Binary systems orbit each other with clockwork precision that enables precise measurements of stellar properties. Variable stars brighten and dim according to physical laws that connect their behavior to the fundamental forces governing all of nature. In the quiet darkness that surrounds us, countless photons continue their ancient journeys from distant stellar cores, carrying information about nuclear fusion, stellar structure, and cosmic evolution. Some of these photons began their travels when our solar system was young, before Earth had developed complex life, before consciousness emerged to wonder about the flickering lights in the night sky. The realization that we can intercept and interpret these ancient messengers represents one of humanity's greatest intellectual achievements. Through patience, ingenuity, and the gradual refinement of our tools and techniques, we have learned to read the stories written in the starlight and to understand our place in the cosmic narrative they reveal. The gentle dance of starlight through our atmosphere connects us to processes that span the entire range of cosmic scales and time periods. The quantum mechanics of nuclear fusion, the fluid dynamics of stellar interiors, the gravitational interactions of binary systems, and the large-scale structure of galaxies all contribute to the subtle variations in brightness that we can now measure and interpret with extraordinary precision. This comprehensive understanding has transformed our perspective on the universe and our place within it. We are no longer passive observers of distant lights, but active participants in a cosmic community governed by universal physical laws. The elements in our bodies, the energy that powers our civilization, and the information that fills our minds all connect us intimately to the stellar processes that continue shaping the universe around us. The precision with which we can now study these processes provides a foundation for understanding phenomena that operate on even larger scales. The same techniques used to measure stellar oscillations are now being applied to study the cosmic microwave background radiation, the distribution of dark matter, and the acceleration of cosmic expansion. Future observations will extend our reach even further into the cosmos and deeper into the past. Next-generation space telescopes will observe the first stars that formed in the early universe, study the assembly of the first galaxies, and search for signs of life in the atmospheres of potentially habitable worlds orbiting nearby stars. The technologies required for these future missions continue to push the boundaries of human engineering and scientific capability. Yet each advance builds on the foundation laid by previous generations of observers who patiently studied the flickering of stars and gradually developed our understanding of stellar physics and cosmic evolution. The story of stellar variability research thus serves as an inspiring example of how human curiosity and persistence can lead to profound discoveries about the nature of reality. From the earliest observations of changing star brightness to the current searches for biosignatures in exoplanet atmospheres, each generation has contributed to our growing comprehension of the universe. As consciousness fades and the gentle rhythm of cosmic processes carries you toward peaceful rest, let the knowledge of these deep connections provide comfort and perspective. The same nuclear fusion that powers the stars also powered the formation of the elements that compose your body. The same gravitational forces that hold stellar systems together also guide the circulation of blood through your veins and the electrical activity that generates thoughts and dreams. In the soft glow of starlight filtering through our restless atmosphere, we find not just beauty and wonder, but profound evidence of our connection to the cosmos and our participation in the ongoing story of stellar birth, evolution, and death. The flickering stars carry messages of cosmic history and cosmic future, written in the universal language of physics and decoded through centuries of patient observation and careful analysis. Tonight, as stellar photons complete their journeys across space and time to reach your eyes, they bring with them the accumulated wisdom of cosmic evolution and human discovery. In the gentle dance of starlight through Earth's atmosphere, we witness the intersection of terrestrial and celestial phenomena, a reminder that we belong to something far grander and more beautiful than any single world could contain. The knowledge that we can read these cosmic messages, understand their meaning, and share their insights across generations represents one of the most remarkable achievements in the history of human thought. Through the study of stellar flickering, we have not only learned about the stars themselves, but also discovered profound truths about matter, energy, space, time, and our own remarkable ability to comprehend the universe of which we are all part. In this quiet moment between wakefulness and sleep, surrounded by the gentle light of distant suns, we rest in the peaceful knowledge that we are connected to cosmic processes that span billions of years and countless light years of space. The tiny fluctuations in stellar brightness that we can now measure with extraordinary precision carry stories of stellar birth in vast molecular clouds, nuclear fusion in stellar cores, and the dispersal of heavy elements that make planets and life possible. The atmospheric turbulence that creates the gentle twinkling we observe serves as a bridge between our earthly existence and the vast cosmos beyond. In those final moments before starlight reaches our eyes, it carries with it not just information about distant stellar furnaces, but also a reminder of our intimate connection to the physical processes that govern the universe from its smallest to its largest scales. As sleep approaches and the busy thoughts of consciousness gradually fade into peaceful rest, the steady pulse of stellar oscillations and the soft dance of light through moving air can serve as a gentle lullaby, reminding us that we are part of something ancient, beautiful, and wonderfully comprehensible. The stars that twinkle overhead are not distant strangers, but cosmic neighbors whose stories we have learned to read, whose secrets we have patiently uncovered, and whose light connects us to the deepest mysteries and most profound truths about the universe we call home. Through the infinite silence of space, stellar radiation continues its eternal journey toward Earth, carrying within each photon the accumulated stories of cosmic time. As these ancient messengers of light traverse the final miles of their voyage, they encounter the delicate boundary where space meets atmosphere, where the vacuum of eternity gives way to the gentle embrace of our planetary cocoon. The process that unfolds in these last moments before starlight reaches human consciousness operates with a precision that spans scales from the microscopic to the astronomical. Water vapor molecules suspended in the upper atmosphere create tiny lenses that focus and defocus passing light beams. Temperature gradients between different air masses bend stellar radiation along curved paths that change from moment to moment. Pressure variations caused by distant weather systems create pockets of varying density that act like moving prisms in the sky above us. These atmospheric effects reveal themselves most dramatically when we observe stars positioned near the horizon, where their light must traverse the maximum possible thickness of Earth's gaseous envelope. A star directly overhead passes through perhaps 60 miles of atmosphere before reaching our eyes. But a star hanging low in the evening sky, barely clearing the distant hills, sends its light through hundreds of miles of increasingly dense air, encountering layer upon layer of thermal boundaries and wind shear zones. This extended journey through multiple atmospheric layers creates the most pronounced twinkling effects, transforming steady stellar beacons into rapidly changing points of colored light. The physics governing these changes operates on multiple timescales simultaneously. Rapid fluctuations occurring several times per second result from small-scale turbulent cells moving across the light path. Slower variations happening over minutes or hours reflect larger weather patterns and thermal changes in the atmosphere above. The colors we sometimes observe during intense stellar scintillation reveal fundamental properties of light itself and the way different wavelengths interact with matter. Blue light, carrying more energy per photon than red light, bends more readily when passing through atmospheric density variations. This differential refraction can temporarily separate starlight into its component colors, creating brief flashes of red, blue, and white that dance across our vision like tiny rainbows flickering in the darkness. Understanding these atmospheric effects required centuries of patient observation and theoretical development. Early astronomers recognized that the quality of stellar images varied dramatically with weather conditions, altitude, and time of night. Mountain observatories were built specifically to escape the densest layers of atmosphere and achieve steadier viewing conditions. Desert locations were chosen for their thermal stability and low humidity. Island sites were selected for their isolation from continental weather patterns. Yet even the best earthbound observing conditions impose fundamental limits on the precision with which stellar properties can be measured. The constant motion of atmospheric turbulent cells creates a continuously changing pattern of distortion that blurs stellar images and introduces noise into brightness measurements. A star that should appear as a perfect point of light instead shows up as a fuzzy, dancing blob, whose apparent size and shape fluctuate unpredictably. The breakthrough that revolutionized stellar astronomy came with the development of space-based observatories positioned beyond Earth's atmospheric interference. From the perfect vacuum of space, stars appear exactly as they truly are, steady points of light whose brightness and color reflect only their intrinsic properties. The absence of atmospheric turbulence allows measurements of extraordinary precision, revealing subtle variations that would be completely lost in the noise of atmospheric scintillation. This transition from ground-based to space-based observations marked a fundamental shift in our understanding of stellar behavior. What had seemed like random flickering caused by atmospheric effects was revealed to contain systematic patterns that encode information about stellar structure, evolution, and internal dynamics. The same stars that appeared to twinkle chaotically when viewed from Earth's surface displayed regular, predictable variations when observed from space. These intrinsic stellar variations operate on timescales vastly different from atmospheric scintillation. While atmospheric effects create brightness, changes occurring many times per second, real stellar variability unfolds over minutes, hours, days, or even years. The distinction between these different types of variation requires careful analysis and sophisticated observational techniques that can separate atmospheric noise from genuine stellar signals. The most common type of intrinsic stellar variability results from pulsations driven by instabilities in stellar structure. As stars evolve and their internal composition changes, they sometimes enter phases where the balance between gravitational contraction and radiation pressure becomes unstable. The star responds to this instability by expanding and contracting rhythmically, like a vast cosmic heart beating with periods that can range from minutes to years. The physical mechanism driving these pulsations involves complex interactions between stellar structure, nuclear burning rates, and radiation transport. When a pulsating star contracts under its own gravity, the interior becomes denser and hotter, increasing the rate of nuclear fusion reactions. This enhanced energy production causes the outer layers to expand and cool, which reduces the opacity and allows more radiation to escape. The decreased radiation pressure then allows gravity to pull the star back together, restarting the cycle. Different types of stars exhibit characteristic pulsation patterns that reflect their mass, age, and evolutionary state. Young, hot stars show rapid oscillations with periods of minutes or hours, driven by pressure waves propagating through their dense interiors. Older, cooler stars display slower pulsations with periods of days or months, reflecting their larger size and lower internal temperatures. The most evolved stars can show pulsations lasting years as they undergo the final stages of stellar death. Cepheid variable stars represent one of the most important classes of pulsating variables, both for their astronomical significance and their role in measuring cosmic distances. These massive luminous stars undergo regular brightness variations, with periods ranging from a few days to several months. What makes Cepheids particularly valuable is the tight relationship between their pulsation periods and their intrinsic luminosities, discovered in the early 20th century through careful observations of stars in nearby galaxies. This period luminosity relationship allows astronomers to determine the true brightness of any Cepheid, simply by measuring how long it takes to complete one pulsation cycle. By comparing this intrinsic brightness to how bright the star appears from Earth, the distance can be calculated with remarkable precision. Cepheids thus serve as cosmic lighthouses, allowing us to map the three-dimensional structure of our local galactic neighborhood and measure distances to nearby galaxies. The discovery of the Cepheid period luminosity relationship fundamentally changed our understanding of the universe's scale and structure. In the 1920s, Edwin Hubble used Cepheid variables in the Andromeda Galaxy to prove that it lay far beyond the boundaries of our own Milky Way, establishing that spiral nebulae were actually distant galaxies containing billions of stars. This observation doubled the known size of the universe and laid the foundation for modern cosmology. Hubble's subsequent work with Cepheids in many galaxies revealed an even more profound discovery. By measuring distances to galaxies using Cepheid variables and comparing these distances to the galaxy's recession velocities determined from spectroscopic observations, he discovered that the universe itself is expanding. More distant galaxies are moving away from us faster than nearby ones, exactly as predicted by Einstein's theory of general relativity for an expanding universe. The precision required to make these fundamental discoveries depended critically on understanding and correcting for the effects of atmospheric turbulence on stellar observations. The same scintillation that creates the gentle twinkling we see with our eyes also introduces systematic errors into brightness measurements that must be carefully accounted for when studying variable stars. Advanced statistical techniques were developed to separate real stellar variations from atmospheric noise, enabling the precise measurements needed for distance determinations. RR Lyrae stars represent another important class of pulsating variables that serve as standard candles for measuring galactic distances. These older, less massive stars have shorter pulsation periods than Cepheids, typically less than 1 day, and show smaller amplitude brightness variations. What makes RR Lyrae stars particularly valuable is that they all have approximately the same intrinsic brightness, making them excellent distance indicators for studying the structure of our own galaxy. The distribution of RR Lyrae stars throughout the Milky Way has revealed important details about galactic structure and evolution. These stars are found primarily in the galaxy's halo and bulge regions, where they trace out the three-dimensional shape of our galaxy's oldest stellar populations. Their uniform brightness allows precise distance measurements that have mapped the galaxy's spherical halo and revealed evidence for past galactic mergers that disrupted the original stellar distribution. Long-period variable stars, also known as mirror variables, represent the final evolutionary stages of stars similar to our Sun. These aging red giants have exhausted the hydrogen in their cores and are now burning helium in surrounding shells, a process that makes their structure inherently unstable. The resulting pulsations can cause brightness changes of factors of hundreds or thousands over periods, ranging from several months to several years. Mirror variables are particularly important for understanding stellar evolution and the chemical enrichment of galaxies. As these stars pulsate, they shed material from their outer layers through powerful stellar winds, enriching the surrounding interstellar medium with heavy elements created through nuclear fusion in their cores. This process of mass loss eventually exposes the hot, dense core of the star, which becomes a white dwarf surrounded by an expanding nebula of ejected material. The study of mirror variables has revealed the complex relationship between stellar mass, age, and pulsation properties. More massive stars evolve more rapidly and reach the mirror phase sooner in their lives, while less massive stars take billions of years to exhaust their core hydrogen and begin pulsating. The chemical composition of the ejected material reflects the nuclear burning history of each star, providing insights into how different stellar masses contribute to galactic chemical evolution. The observation and analysis of variable starlight curves requires sophisticated techniques that can extract meaningful information from noisy, complex data sets. Modern astronomical surveys monitor hundreds of thousands of stars simultaneously, recording their brightness variations over months or years with precision measured in parts per million. The resulting light curves contain information about pulsation periods, amplitude variations, and subtle changes in pulsation characteristics that reveal details about stellar structure and evolution. Machine learning algorithms are increasingly used to analyze these vast databases of stellar variability, identifying patterns and relationships that would be impossible for human astronomers to find manually. These automated systems can classify variable stars by type, detect rare or unusual objects, and even discover new classes of variable stars that don't fit existing categories. The combination of high-precision photometry and sophisticated analysis techniques is revolutionizing our understanding of stellar behavior and evolution. The internal structure of pulsating stars can be probed through asteroseismology, the study of stellar oscillations analogous to the seismology used to study Earth's interior. Just as earthquakes create waves that reveal our planet's internal structure, stellar oscillations create pressure waves that travel through stellar interiors and provide information about conditions at different depths. These oscillations manifest as tiny brightness and velocity variations that can be detected with space-based photometry and high-precision spectroscopy. The Sun serves as our primary laboratory for astroseismic studies, with millions of oscillation modes operating simultaneously to create a complex pattern of surface motion. Different oscillation modes penetrate to different depths within the solar interior, allowing astronomers to map temperature, density, and composition from the core to the surface. These measurements have confirmed theoretical models of solar structure and revealed details about the Sun's rotation profile, magnetic field, and nuclear burning rate. Similar astroseismic techniques are now being applied to thousands of other stars, revealing the internal structure and evolutionary state of stars across a wide range of masses and ages. The oscillation frequencies of a star depend on its internal density distribution, which changes as the star ages and consumes nuclear fuel. By measuring these frequencies with high precision, astronomers can determine stellar ages with uncertainties of just a few %, dramatically improving our understanding of stellar evolution timescales. The gentle flickering of starlight that has guided our journey tonight represents far more than a simple atmospheric curiosity. In learning to read the subtle language written in these tiny variations of brightness, we have unlocked one of the universe's most profound libraries of knowledge. From the ancient astronomers who first noticed that some stars change their glow over time, to the modern space missions that monitor millions of stellar heartbeats simultaneously, humanity has transformed the soft dance of starlight into a comprehensive understanding of cosmic evolution. Each photon that completes its journey from distant stellar cores to reach your eyes carries within it stories spanning billions of years and vast distances beyond imagination. The same atmospheric turbulence that creates the peaceful twinkling we observe has motivated our greatest technological achievements in astronomy, driving us to build observatories in space where the universe reveals its true nature with crystal clarity. Tonight, as you rest beneath this gentle canopy of distant suns, remember that you are witnessing the intersection of earthly and cosmic phenomena. The flickering stars above are not just beautiful decorations scattered across the darkness, but cosmic neighbors whose light connects us intimately to the fundamental processes that govern all existence. In their soft dance through our restless atmosphere, we find not just wonder, but profound evidence of our place in the vast, interconnected tapestry of space and time.